When we talk about light, we don't just talk about sunlight. Light comes from many sources and takes many different forms. In fact, many forms that you see every day and didn't even realize they were light. Light exists on an entire spectrum called the electromagnetic spectrum. All different forms of light, from radar to visible light, travel at the same intergalactic speed limit, the speed of light. To expand our understanding of light, let's connect it back to something we know: waves. Light acts as a wave. More specifically, an electromagnetic transverse wave. Transverse waves are the waves that we've studied when we studied mechanical waves. These waves have crests and troughs. They have wavelengths that span a distance from a crest to a crest. They have amplitudes relative to the amount of energy, and they have frequencies that have specific meaning to the type or form of light. These electromagnetic transverse waves are caused by two separate waves, one electrical, one magnetic, vibrating at the same time. As we continue to explore physics, we'll see that electrical fields and magnetic fields continue to share this special bond and connection. These two fields run perpendicular to one another, creating a light wave, composed of both an electrical field and a magnetic field wave. This is where we get the term electromagnetic wave. Light does not need a medium to travel through. We observe it traveling through air every day. It can pass through water. But at the same time, we see that light can travel even through the depths of outer space, where there's no atmosphere, no material, it's a vacuum. No medium whatsoever. All light travels at exactly the same speed. Whether it's a radio wave, visible light waves, or even gamma radiation, it all travels at this intergalactic speed limit, 3 times 10 to the 8th meters per second. This is roughly 300 million meters per 1 second. Imagine your typical meter stick. Now imagine 300 million of them. Imagine any object or anything that can travel that entire distance in one single second. In fact, that becomes the challenge. Because light is traveling as a wave, it's traveling as energy, we don't have to worry about mass traveling at that speed. However, light travels as a particle as well. There's a duality between light as a wave and light as a particle. The model of having light as a wave and light as a particle help to explain how light behaves. We have to understand light as a particle as well, because light waves can't explain all of light's behaviors. Light acts as a wave and a particle at the same time. This particular particle, or very, very submicroscopic element or piece, is called a photon, a light particle with no mass that travels in a transverse light wave. If you can imagine the wave as the energy that's pushing behind a rocket, the photon is the pilot of that rocket. The wave pushes the photon. It has no mass, so there's no concern about it reaching speeds like 300 million meters per second. All light travels at the exact same speed, the speed of light, 3 times 10 to the 8th meters per second. However, if you change the wavelength of a wave, you're going to end up changing the frequencies. Higher frequencies will create lower wavelengths in order to keep that equation balanced, in order to keep the speed the same. So different frequencies and wavelengths create different uses for light, all traveling at that same intergalactic speed limit of 3 times 10 to the 8th meters per second. All light waves exist on a spectrum based on this frequency and wavelength. We call this the electromagnetic spectrum. As you move from left to right, the frequency increases, which means the waves are much closer together. as you can see by the drawing of the waves in the middle of the electromagnetic spectrum diagram. Wavelengths are listed up top. As you move to the right, the wavelength gets smaller. This is logical. As frequency increases, in order to keep the speed the same, the wavelength has to decrease. Radio waves have the biggest wavelengths, where gamma rays have the smallest wavelengths. That's why larger wavelengths to the left side tend to be used for more communication purposes, whereas the further you get to the right, the more we use that light to either see or to see through things, as the wavelength is small enough to penetrate through molecules. So if we increase the frequency, we decrease the wavelength. We see that as it moves to the right. So over to the right we have high frequencies, short wavelengths. This means high energy. Gamma rays have the highest energy on the electromagnetic spectrum. On the far left end, if we decrease that frequency, we decrease the wavelength. Lower frequencies mean larger wavelengths. This means lower energy. Radio waves are very large and emitted throughout the Earth for communication with cell phones, radio, Doppler radar. Even Bluetooth is a form of radio. These waves, however, have such a low energy that they cause little to no proven major damage to humans, whereas gamma radiation with its high energy creates the Incredible Hulk. The frequency is often attributed to the use or function of the light wave, so it's used for radio or for X-rays, for example. Let's begin by talking about each of the different types of light forms that we see on the electromagnetic spectrum. We'll start at the far end, where we have low energy, a long wavelength, and pretty low frequency. This is light that we can't see. Radio waves give us the largest wavelength. They're also the lowest frequency. They're used to transmit communication signals, cell phones, television signal, Bluetooth, anything that is using some kind of wireless signal, even wireless internet, is using a radio signal. The frequency for radio waves runs between 300 gigahertz and 3 hertz. The wavelength runs a big spectrum from 1 small millimeter to 1 kilometer. It's the size of radio waves that makes them so useful when communicating wirelessly over long distances. We use radio waves that have a size from the point of a pencil to being as long as a football field, depending on the type or form of communication we need. Microwaves are the next highest frequency and the next smallest wavelength. Microwaves are used for communication as well as, more famously, cooking food. Microwave the machine works because microwaves the waves are the right size to vibrate water molecules in food, creating heat. This creates a transfer of radiant energy into thermal energy, heating up the food. The frequency for microwaves is about 300 megahertz to 300 gigahertz. So it's getting slightly smaller slightly bigger as we go. Our wavelength gets slightly smaller as we go. So now we're down to 1 millimeter to about 1 meter, which is 1 meter stick. The next range of light is infrared light. Infrared light still is not visible to the human eye. It's light in the form of heat. So we can either create infrared heat, as some kitchen appliances now do, or we can use it to detect heat. Anything that is heat-seeking or heat vision-based is detecting or sensing infrared light. We also see it used in television remote controls. Next time you pull out your remote control, turn on the camera on your smartphone. Click a couple of buttons. You'll notice that you can see a light blinking on the front end of the remote that you can't see with the human eye. Your camera on your phone, most cameras on phones at least, is able to sense infrared light, whereas the human eye still cannot see it. This is still a form of light, but it's not visible yet. Infrared, so it's under red. The frequency runs about 3 times 10 to the 13th hertz, so it's getting bigger as we go to the right. Our wavelength, though, is getting smaller and smaller. Now we're down to 1 millimeter to 750 nanometers. It's about the size of a cell. Visible light is the range that we know. Visible light is what sunlight is. It's why we can see things. So this is the range that creates light that we can see with the human eye. In fact, the only reason we see color at all is because certain materials can reflect certain colors. All of that light is existing in this same wavelength, this white light wavelength. We perceive it as white light, or sometimes referred to as clear light, but all the different colors of the rainbow exist. Different colors have different frequencies and wavelengths. If we diffract them out, like in a rainbow, we can see all of those different colors. They follow rainbow order, so we can look from lowest frequency to highest frequency, highest wavelength to lowest wavelength for visible light. We have RGB, which stands for red, orange, yellow, green, blue, indigo, violet. Those are the colors, or the frequencies, in order from lowest frequency to highest frequency of visible light. RGB tells us the frequency order as well as the wavelength order. The wavelength gets shorter and shorter to the right, so red has a longer wavelength than violet light. Violet light also has a lot more energy than red light, but they all move at the exact same speed, 3 times 10 to the 8th meters per second. The frequency for visible light spectrum runs at about 4 to 7.5 times 10 to the 14th hertz. So when we start seeing scientific notation like this, we know we're dealing with very big or very small numbers. We have increasingly big frequencies. Likewise, we're going to have increasingly small wavelengths. We're down into the nanometers. That's about the size of bacteria. Ultraviolet light gets us back out of the range that the human eye can see. We often think of ultraviolet light as coming from the sun. This is the light that causes sunburn and suntans. Most of that light is blocked by the ozone layer because the light reflects off the outer layer of the ozone, but some refracts in. This is why we use sunscreen to block the remaining ultraviolet rays. We also see ultraviolet light in black lights. This is what causes phosphorescent materials to glow under a black light, like a laser tag arena. Frequencies run between 7.5 times 10 to the 14th to 3 times 10 to the 16th. As that exponent goes up, we know that the frequency is getting bigger and bigger. So there's more waves per second, which means the wavelength has to keep getting smaller and smaller. We're getting even lower on that nanometer scale. This is about the size of a protein or a virus at this point. X-rays are the next highest frequency, next lowest wavelength. These are still invisible to the human eye, and as we get further to the right, we know that they have higher energy, which allows us to penetrate opaque items or objects. Opaque means it's not see-through. A table is opaque. A piece of glass is clear. It's not opaque or transparent. Medical X-rays are the most common use of X-rays. Just like microwave ovens, they get their name from the type of ray that we're using. We can even use X-ray images of the sun to predict solar flares. The frequency for this range runs about 3 times 10 to the 16th hertz and up. So we're getting such a high frequency that we stop measuring. It's way up there, which means the wavelength gets insanely small. We're down even below 1 whole nanometer. As the frequency increases, the wavelength decreases to keep the speed of light the same. This is getting about to the size of water molecules. Gamma rays are the highest energy, highest frequency, lowest wavelength that we have in the electromagnetic spectrum. They're even more penetrating than X-rays. Their wavelength is small enough to pass through the nucleus of an atom. They're often given off during nuclear explosions. They're powerful enough to pass through almost anything, which means they're powerful enough to pass through humans, to pass through our cells. There's a lot of great medical applications for gamma rays, but a lot of dangerous applications. Because we can, for medical purposes, mutate cells, but also high levels of gamma radiation can mutate cells in unexplained and undesired ways. It's science fiction, but the Hulk was mutated using gamma rays. There's some slight semblance of science behind that. The frequency for these rays is greater than 10 times 20 hertz, so huge frequencies. These waves are traveling one just after another, whereas their wavelength is insanely small. That's why they can pass through almost any object. All of these different lights all travel at the speed of light. The speed of light is constant. It's always the same. On any planet, on any part of the galaxy that we've observed or know of. It's represented by the letter c, or the variable c. This is the same c of E equals mc squared, famously noted by Albert Einstein. Again, it's represented as 3 times 10 to the 8th meters per second. This is a rough rounding of about 299 million meters per second. Galileo first discovered, or first assumed, that there was a speed of light in the 1620s. He set an assistant across to a far-off hill. When he turned on his light, his assistant was to turn on his light as well. They were trying to find the speed of the light. What they were really recording was the speed of their reactions. Galileo said that in his time, they would never discover the speed of light. This was almost a challenge to future scientists. In fact, theories like the speed of light got Galileo in a lot of trouble with the church. He was labeled a heretic. Hundreds of years later, though, knowing that there is a measurable speed of light, this middle finger is on display in a science museum in Italy. It's Galileo's retribution for being told that he was wrong, when we see now how right he is. Following about 50 years later, Romer tried to do the same test, tried to find a speed of light. He noticed that compared to the angle of the Earth, a certain moon of Jupiter could be seen at a different time for when it was supposed to be in the Earth's line of sight. What he discovered is that that light was taking a different amount of time to get to our eye. By using the calculated time of when the light should have been seen and when it was actually seen, they were able to calculate the distance between that moon and the Earth, use that time, and calculate a very rough speed of light. It wasn't until later, years later, 1900s, Michelson found a similar way, using reflected light, to find the speed of light that we now know. Because light is moving as both a particle and wave, we can actually treat it very much like any object, from a car to a ball rolling, because we can use the speed formula. This is distance divided by time. So speed, in this case referring to 3 times 10 to the 8th meters per second, distance referring to the distance the light wave has traveled, and time referring to the time it takes for light to travel the known distance. Using this, we can calculate distances of known objects based on light. We can calculate the time it takes light, whether it's in the form of communication waves or visible light waves, to travel a certain distance. Let's try an example. A very common example here. It takes light 8 minutes and 20 seconds to travel from the sun to the Earth. how far away is the Earth from the Sun? If we know this intergalactic speed limit, we don't have to pull out a giant ruler to measure the distance. We can calculate it because light travels the same speed as it travels from the Earth or from the Sun all the way to the Earth. We just use the basic speed formula that we learned first semester. Speed is distance over time. So if I know that that speed has to be 3 times 10 to the 8th, and I know the time is 500 seconds, because 8 minutes is 480 seconds, plus 20 seconds makes 500 seconds, I can calculate for the distance. I just ask myself what's happening in my variable. I'm dividing distance by 500. So to solve for distance, I'm going to multiply both sides by 500. 3 times 10 to the 8th times 500 is going to give me a distance of about, if I put it in scientific notation, 1.5 times 10 to the 11th meters. In real world numbers, because we're using a rounded speed of light, it's closer to 149 billion meters. This is a calculated and confirmed distance that we can solve and explain using basic high school physics.